all, welcome to your very first set of Unit 3 chemistry notes. In this unit, we're going to talk specifically about the electron. Unit 2 is about the atom as a whole. Unit 3 is all about the electron. Specifically, where you can find your electrons and how they behave. In Unit 2, we learned that atoms have a dense nucleus in the very center, and then they have those orbits that the electrons exist in, and they're just nice, neat little circles that the electrons spin around in and just travel around the nucleus, just like the planets travel around the sun in our solar system. And we mentioned the fact that this is not true, right? These are called orbits. Bohr is the one who came up with them. And we talked really briefly in Unit 2 about the fact that this is not how atoms actually work. This is not how electrons actually work. In this unit, we're going to talk about what really is going on. So your electron cloud, instead of being made of those circular orbits we just saw, it is actually made of a complex arrangement of something called orbitals. So it sounds like an orbit, but it's not quite the same thing. These are orbitals. They are three-dimensional regions around the nucleus which indicate the probable location of the electron. We have to say that they are probable locations because electrons are incredibly tiny, incredibly fast, and have wave-like behavior. We're going to talk more about this on day 3 of the unit. For right now, just understand this means that although electrons are matter, they sometimes don't always act like it. It gives them some really weird behavior. It makes them kind of hard to pin down. So instead of just this nice, neat circle, we have to talk about orbitals, which are the probable locations of electrons. Each of these orbitals, each of these three-dimensional regions, are located in a specific main energy level and a sublevel. So every orbital has two things that describe it. It gets a main energy level, which is like a really general location, and then it gets a sublevel, which is a more specific identifier. The main energy levels, they're sometimes also called shells, are indicated by a number. And that number comes from the periodic table. It's indicated by each period or each row on the table. Those are the left and right ones. So as you move down your table, as you get to larger and larger periods, the electron energy and distance from the nucleus increases as the main energy level increases. So what this means is, looking at your periodic table, you have your first row, and it is numbered on your periodic table, says a 1, period 1, period 2, period 3, 4, 5, 6, and 7. And these rows right here, they actually insert into the table right there. So there are 7 rows, there are 7 main energy levels. And as the value of the energy level gets bigger, the energy of the electrons found there increases, and the distance from the nucleus increases. So electrons that are found in this first energy level have a very low energy, because they're in a low energy level, and they're very close to the nucleus. Lower energy level gives you lower energy, and you're closer to the nucleus. Versus level 7 down here, electrons in the 7th energy level have a very high energy, and they are pretty far from the nucleus. Far. At the top of the table in the low energy levels, the electrons found there are low energy, and the electrons are very close to the nucleus. As you increase the energy level of your orbital, the electrons in that orbital have a higher energy, and they are farther from the nucleus. So those are the main energy levels. Now let's talk about our sublevels or subshells. These are indicated with a letter. And that letter indicates the shape of the orbital. They all have very specific shapes. And the electron energy increases as the sublevel increases. As you go through your different sublevels, the energy of the electrons found there increases. So let's look at our different sublevels. Their name is actually just a letter. The name of our first sublevel, the first orbital name is S. They are called the s orbitals. The shape that they take is easy to remember because your s orbitals are spherical, or they have a sphere shape, right? So it's like a circle, but it's 3D, right? Your orbitals are three-dimensional. So your s orbitals have a sphere shape. And there's a very specific place on your periodic table that you can always see your s orbitals. And that is over here on the left in these first two columns of the periodic table. And helium, we sort of pretend, goes right there. So this is the S block. We call these two rows of your periodic table where you find your s orbitals. We call this the S block. Each square of your table here represents an electron. It represents an element. So in each row, in each energy level of your table, there are 1, 2 boxes in the S block. That means there are 1, 2 electrons in an s orbital in each energy level. So that means you can put a maximum of 2 electrons into your s orbital on any energy level. And I will tell you that in each energy level, the number of s orbitals, this is the number of orbitals, the number of orbitals in each sublevel, you have 1 s orbital. So on each row of your periodic table, there is 1 s orbital. It can hold 2 electrons, and it is spherical in shape. That's your first sublevel. Your second type of orbital is called the p orbital. Its name is the p orbital. To help you remember the shape, you can think of it being peanut shaped. It has sort of this dumbbell peanut looking shape. Looking back at our table, your p orbitals are found over here in this section of the table. So this here, this is your p block, all of these elements in here. This is your p block. So if we count in each row of the table, there's 1, 2, 3, 4, 5, 6 boxes in the p block. So that means that in each main energy level, in each row of the table, there are 1, 2, 3, 4, 5, 6 electrons in p orbitals. Each energy level has 6 electrons in the p orbitals. So they can hold a maximum of 6 electrons. Once again, I will tell you that in each level, each energy level, there are 3 p orbitals. So in each row of your table, in each main energy level, there are 3 p orbitals. They can hold a total of 6 electrons. They have a peanut shape. They are called p orbitals. The next set of orbitals, the next orbital name is the d orbital. And the d orbital has sort of this kind of chunky 4-leaf clover shape. We say that it is daisy shaped. Again, the name is d orbital. I'm just calling it daisy shaped to sort of help you remember the shape. And if we go look at our table, the d orbitals are in this middle section, this short section right here. So everything in here falls into a d orbital. And if we count across, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes, that means that we can fit a total of 10 electrons into our d orbitals in any row. So the max number of electrons in my d orbitals are 10. And you may be picking up on a pattern here. The number of d orbitals in any energy level is 5. We can hold 2 electrons in our 1s orbital. We can hold 6 electrons in our 3p orbitals. We can hold 10 electrons in our 5p orbitals. Hopefully you're picking up on a pattern here. Our last type of orbital is the f orbital. I'm not going to try to draw a picture of these for reasons you will see in a second. We can just say that they are funky in shape. Because again, there's really not a good word to describe what they look like. And one more time, looking back at our table, just like your f orbitals are weird in shape, you find them in a weird place on your table. These are your f orbitals down here. And if you count across, you'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 boxes means there are 14 electrons in my f orbitals for any energy level. So I can fit a maximum of 14 electrons, and if you were going to guess, hopefully you would guess that there are 7 of those orbitals in each energy level. So these are your different orbital shapes. Let's talk a little bit more about our orbitals. You can fit a maximum, hopefully you saw this, a maximum of 2 electrons in any single orbital. So we just saw in one orbital we could fit 2 electrons because 1 times 2 is 2. In 3 orbitals we could fit 6 electrons because 3 times 2 is 6. In 5 orbitals you can fit 10 electrons because 5 times 2 is 10. And in 7 orbitals we can fit 14 electrons because 7 times 2 is 14. Each orbital can hold a maximum of 2 electrons. Some might hold 1 electron, some might not hold any, but the most you can fit in any orbital is 2. And then last thing to say about these is that electrons in the highest energy level determine how an atom will react chemically. These highest energy electrons are called valence electrons. And you can determine the number of valence electrons by looking at the family, sometimes also called a group, which is the same as just the column number on your periodic table. We'll do some practice with this later. So let's look one more time at some actual real pictures of your orbitals, better than my beautiful drawings. Here's your s orbital. You get 1 of these in every energy level, and it really is a sphere. Your nucleus would be right here in the center, and then there's sort of an equal chance in every direction of finding an electron around the nucleus. That's your s orbital. Your p orbitals, you get 3 of them in each energy level. So this right here is a single p orbital, and that's a p orbital, and this is a p orbital. So they're all the exact same shape, they're just laid around the nucleus differently. So the nucleus would be at the origin, or like right there, on each of these. So right there, and right here. These are all the same shape, all the same size. They're really identical, they're just laid differently around the nucleus. So that if you put them all in one place, you would have your nucleus, and then 1 p orbital like this, 1 p orbital like this, and 1 p orbital kind of like that. They all exist in the same place, just point in different directions. Then you have your 5 d orbitals. So this is a single d orbital, this one daisy looking thing. And then this is another d orbital. Again, it's the same shape, just laid out in space differently. This one is in the zy plane. This one is in the xy plane. This one is in the xz plane, and then things get weird for naming them. Notice that this one is turned a little bit differently than this one, and then here this is just a crazy shape. But those are your 5 d orbitals, and then your f orbitals get truly strange. You might call this like a corn on the cob holder. These look like balloon animals that have just gone terribly wrong, but these are your 7 f orbitals. 1, 2, 3, 4, 5, 6, 7. And again, your nucleus would be right in the center, right on the origin for each one. And each one of these crazy shapes is only going to hold 2 electrons max. So you might have like an electron there, an electron there. You might have an electron here and an electron there, or you might have one here and one there. The electrons can be anywhere, but there are only going to be 2 in each of these orbitals at the same time. All right, so the next page in your booklet does say practice, but they are actually the same 10 practice problems you're going to see in the next video. So go ahead and give them a go, but I'm not going to put the key up until the next video so that you can do that practice then. All right, orbitals are weird. Electrons are weird. So you may have watched this entire video and not understood a word of it. And that's okay. That's kind of how this unit goes. Push on to the next one. Go over how electrons fill orbitals, get some practice there, and hopefully this will start to click into place a little bit. Orbitals are just places you find electrons. There are lots of different kinds of them. They have different energies. They have different shapes, but they're just places you can find electrons. And that's what we're going to talk about in the next video. So if you found this confusing, don't be discouraged. Don't give up. Push on, watch the next one, and hopefully it'll make a little bit more sense there. Good luck.